So we want to find the applied force P that we need to apply to keep it in equilibrium, and the reactions, all the reactions at A and at B. So for the free body diagram, they have the origin of the system at A, so I'll just keep it at A. So what's the object of interest here? So what are we isolating from the rest of the connections, all of its connections, and representing in our free body diagram? Right, so the orange or the yellow shaft here, we're going to free it from the bearing at A, free it from the bearing at B. It'll have these two applied weights, forces on it also. So the orange shaft is what we are drawing as our object. So A, the point A is already on here. That's going to be the origin and also a bearing, so we'll fill that in a minute. It passes through that other bearing at B that we'll have to model. So B is going to be located at 0.280 inches. We have that applied force of 80 pounds. Acting at a point that I'll call C, which is at -10, -14, 0. A is at the origin, and then we're applying a force P that's parallel to the x-axis, and we're going to be applying that at a point D that is 0, -10, -8 inches. So I include the two applied forces, the 80 and this force P that ultimately we need to find. So we need to know what's happening at A and what's happening at B. So A and B are both bearings, but again, there's a difference between a journal bearing and a thrust bearing and what motion they allow. So A, they say, is a journal bearing. So how does the journal bearing differ from the thrust bearing? Right, so as far as where they differ is the translation of the shaft. A journal bearing, the shaft is allowed to pass in its longitudinal direction through it. In a thrust bearing, it cannot. It's halted there. They both provide forces perpendicular to the direction of the shaft, though. So at A, it's allowed to move in the y direction, the shaft is, so there's no AY, but it can't move perpendicular to the y direction. So we can model that as a force AX and a force AZ. I'm going to assume they're both positive. All right, so as far as forces go, that's what the journal bearing gives us. It'll be, in this case, an X and a Z force. They tell us that the bearings are properly aligned, meaning that there's two bearings here. When properly aligned, the bearings do not exert a couple or a moment on the shaft. So as far as A goes, only those two forces, no couples on the shaft. So two reactions at A. And then at B, what is going to be the reactions we have at B? What's prevented from, what motion's prevented? Right, so B is the thrust bearing. So the shaft cannot move in its longitudinal direction, which is the y direction. So we'll have a BY. And it can't move perpendicular to its longitudinal direction, so we can model that as a BX and as a BZ. Again, these two bearings are properly aligned, so neither one exerts a couple on the shaft. So if we look at our free body diagram here, we have AXAZ, BXBY, BZ, and P as our unknowns. So 6 unknowns, and we can get up to 6 linearly independent equilibrium equations out of it. In this case, we don't need any of our unit vectors because everything, all forces, act along a coordinate direction, so x, y, or z. So we can jump right into making our equations, our equilibrium equations. So in the x direction, we have that ax. We have a bx. Both of them I assumed were positive. And our applied force P, that's in the negative x direction, so minus p. In the y direction, we just have by. So from equation 2, by is 0. It can stop motion in the y direction, but under this loading condition with this AD and this force P, it turns out that by is 0. But it doesn't mean that we shouldn't have drawn it. It does prevent the motion. Just under these conditions, it doesn't want to move in that direction. Then the z, we have our AZ, we have our BZ, and then we have negative 80 from the applied load at what I called C. So I've used equation 2. I have equation 1 and 3, so I have 2 equations, but I still have 5 unknowns. So I was able to find one of them, but 5 unknowns left, 2 equations. So I have to go on to the moment about point to get 3 more equilibrium equations to be able to solve this. Right, so looking at our free body diagram, what point looks like the best to take the moment about? Right, so I would say in general, B, because BX, BY, BZ act there. If we also look at A, we have 2 unknowns there. In my notes, I actually chose A. I would say just based on the number of unknowns, B is probably better if you don't look at anything else. But we already know that BY is 0, so actually one of these things we already know. So I would, if I did this again, I would choose B, but in my notes I chose A. It's going to turn out that both of them are equally good. Right. And just how I named it point D. But right, so the location where P is, I called it D in my notes. So RAD cross negative PI. Right, so that is the moment due to the applied force that we're looking for. What else causes a moment around point A? Right, or K in this case. So RAC cross negative 80K. So due to that applied 80-pound force, that's the moment around A. And then what else will cause a moment around A? Yeah. Right, so at B, this is where we can save ourselves a little bit of time and effort. There's actually 3 forces that act at B, at least according to my free body diagram, BX, BY, BZ. I'm going to collectively call that vector B. So this, because they're all acting at the same point, instead of doing 3 separate cross products for each force at B, I can just do 1 cross product and have each of the components of that force inside of it. So it's a little bit of condensing this way. Yeah.
Would that be similar to the test question where you could sum the vectors at that point?
Right, exactly. So since there were multiple forces at that point, RAB cross this, plus RAB cross that, plus RAB cross this, we can factor out that RAB and just add those 3 forces together. So the same as in the test, you could add all the forces together and then take the components. This one's easier because each one only has an I, a J, or a K component. So it's just a little bit simpler to do it this way. So if I expand this out 1 step, all of our measurements here are going to be in inches. All of our forces are going to be in pounds. So from the first cross product, we have negative P, 0, 0. And that's at 0, negative 10, negative 8. Spanning out the second one, that's going to be, again, inches and pounds. So negative 80, 0, 0, or 0, 0, negative 80. And RAC, just taking a step back, also taking the moment about A rather than B is good, because A is the origin, so the position vectors are just easier to find than if we took the moment about B. So with that, combined with the 2 forces at the A, moment about A is a little bit easier. For RAC, we get negative 10, 14, 0. And then for the last cross product, so this is how we condense our efforts a little bit. This is where now B I break up into its components. Because I already know that BY is 0, I'll put it right in there. But again, we'll see at the after this step that it would drop out anyway, because if we look at the position vector from A to B, it's 0, 28, 0. So I won't go through all the steps here, but if I did not put the 0 in, and I did write by, if you picture the cross product, I have a 0 row in the cross product, so everything is going to be 0 out of it anyway. But since I know its value, I can put 0 in. All right, so bx and bz both in that same term. All right, so I won't go through the intermediary steps, but I expand out these three cross products, group the i's, the j's, and the k's, and then I get out of it, grouping the I terms together, the coefficient in front of I get negative 1120 plus 28bz. For the j terms, I get negative 800 plus 8p. And for the k terms, I get negative 10p minus 28bx. So yeah, I skipped the step, but this is the coefficient in front of the I after the expansion of the cross products, in front of the j, and in front of the k. So these work out nicely for doing it by hand. If we look at equation 4, we can get bz right out of there. So bz, we get 40 pounds. Equation 5, p is the only unknown. So the applied load is 100 pounds.
Is that a negative 10 for the K?
This is, yes, negative 10p. Negative 10p minus 28bx. We know bx from, we know p from equation 5, so we can get bx out of here. So we get that bx is negative 35.7 pounds. Four unknowns we have solved for. We can now go up to equation 1. We know p, we know bx, so we can get ax out of this. Ax, we get 136 pounds. And finally, we know bz, so we can go up to equation 3, and we can find az is 40 pounds.